thing, do you know flashing? Flashing. Flashing, of course. Flashes also, there is a flash. Camera, there are flashes, there is a flash. So that is a flashlight. Flashlight means it's a sudden, very intense light coming for a very short period of time. It's a flash. Yeah. This one, eh? Yeah. So good example for flashing is the camera flashlight. Even you cannot notice when it's on and when it's off, but suddenly there is a very intense bright light comes and goes. Yeah. So that is one of the very good example for flashing. And in refrigeration also there is a flashing effect. So this one we should understand. So I'm going to share with you because these practical points are very important. That's why I'm going to share with you one example. Let's see. Something like this. This is a drop of water, let's say. So today we are going to learn several flashing examples. Yeah. It's a drop of water. It's a tiny bit, but I made it a little bigger for us to see in the screens and all. And let's say now, so today we have to live with this problem, Putana. No choice. We have to live with this problem because I'm experiencing this even yesterday. So I made a complaint also to Telecom, but no one came to rectify that because we have the full data because month starts. So we have over 40 GB, but now the signals interrupting in very unacceptable ways. And let's say here, a hot plate. Okay, hot plate means, of course, I put this is at bit high temperature, 120 hot plate. So this is normal ambient. So normal ambient means your pressure is 1 bar. So the best is to say 1 atmospheric. So that is the better terming, but what at 1 atmospheric is closer to 1 bar. Okay. So this one, you know that at 1 bar, water means you know well about that. Even the boiling point is 100. So let's say BP, I just put as BP, 100 degrees Celsius. So having known everything here, we are going to let this drop on the hot plate. Okay, drop on the hot plate. So what happens? So hot plate means this is 120. 120. 120. So immediately what's happening is, let me draw that one as well. Don't worry, Bhutan, today no choice, as I mentioned to you. Immediately this, how to say, this drop of water, okay, becomes flattened, okay.
Jauh, ware. So,
I have changed to mobile data, otherwise we cannot manage it. Now should be all right. So at no time this turns into something like a film, okay. This turns into something like a film. Okay. At no time, it's immediate. This becomes flat like a film. And the situation is now for this heavier hot plate mass. For this heavier hot plate mass at 120. So this 120 remains the same, and this film exposed to this 120. I'll just make it bit. Exposed to this 120 immediate. Okay, so at no time. Yeah. So that's the point, at no time. So if you take a time delta t, it is almost 0. So what happens is this water droplet turned into a little flat film immediately, okay, immediately becomes gas, okay, immediately becomes gas. See the difference. Initially a negligible volume finally becomes a huge gas bubble, okay. So this happens at no time. So this turns here. I think better not to have this maybe. So you can understand what happens. So this is same like a flashlight. All of a sudden, a huge gas bubble forms. But light, of course, once lights off, that is no more you can see the flash. But here, this is the possibility. So this is so violent that molecules are looking for the space so violently that even you may hear the noise like truss. Yeah, it's like that. Okay, so this is a flash. This is a flash. Okay, flashing example, this one. So this is a flash. So if you consider volumes, you can say the volume increases is 1,000 times. This one, volume. Because when it comes to liquid and the vapor densities, volume increases more than 1,000 times here. Okay. And this temperature is, let's say it is 120. Okay. 120, even just for a moment. Just for a moment, this will be 120. Okay. So you can see at no time converts this bubble into this. So this is what you are noticing. Right? This is what you are noticing. And I will put some facts here. I will put some facts here. This is from the steam property table. I'm circling here. At the pressure of 1.9853 bar, the saturation temperature, the boiling temperature is 120. At the pressure of 2.04 bar, almost this is around 2, the boiling temperature, the saturation temperature is 121. So we would say 120 is the boiling temperature at 2 bar. But now at 1 bar, 120 means at 1 bar boiling is 100. So at 1 bar 120 means this is surely superheated. This is surely superheated, and this is something like a gas. Okay? Something like a gas. So at 100, if you put this one, maybe you can see still the same flashing, but it's under saturation. Okay? So this 20 degrees Celsius, this 20 degrees Celsius, okay, this is subcooled. Subcooled means below the saturation. Okay, below the saturation condition means below the boiling point. Subcooled 20 degrees. Okay, this is superheated. You may know that. $120. So boiling point also here is 120 Siemens. This is saturated at 1 bar. Always for saturation, the pressure and temperature going together. Okay, so you have learned some key words as well. The subcooled, the superheated, the saturated, and also about the pressures. Okay, about the pressures. So superheated, okay, at 1 bar. 1 atmospheric, that is the best. Okay, at P equals 1 bar, let's say. P equals 1 bar. So I believe you have some good understanding on this. So I'm putting the same slide. It's the same. So flashing becomes the sudden volume increase. This one I just put this. When liquid evaporates at no time, of course. So flashing related to liquid. Okay, it's related to liquid. So this is related to liquid. That is one thing. Not very clear. Yes. Evaporate at no time. Okay. So here when it comes to liquid. So for light, flashing is different. Even for heat, there can be flashing. Okay, heat also there can be flashing. In the bombs, in detonations, you will see flashing, the thermal flash. Okay, thermal flash. Yeah. So thermal flashing is, there may be applications we may not know. Thermal flashing is suddenly same like light appearing of heat. Okay. I think you may experience that when you fry, let's say you put into the pan some oil first, frying using oil. Let's say you are putting some oil to the frying pan and let the flame on. And after little time, you can hear this little bit boiling like temperature. The oil feels like boiling, but it's not boiling because you are not letting oil to boil that fast, because it has some little safety issues. Because once boil, and if there is a fire nearby, even there can be a fire on the fan, on the pan. Even some Chinese cooking, they do that kind of things as well. So for that boiling oil, sometimes you put this onion and all, and immediately you hear this truss noise, flash noise. What is that? Because the water there, water in onion and all, there is a kind of water. Water, somehow there are water, even the wettability, or even you have not seen, but there are water. 80% water in vegetables and all. So once you put in water, boiling point is 100, but the oil temperature is above 100, maybe 100 or above at that time. So you will hear the same truss noise. That's the flashing of water there. Flashing of water. So when the water flashes means it evaporates suddenly. See, very nice. Even If you are keen on food processes, maybe that can be very wonderful process to try out some food innovations, maybe. Who knows? Yeah. So this is about flashing. Okay. Sudden volume increase, the boiling. Okay. Now we are going for one more example. Let's say same way here. So I take all out. Okay. Now I will take a cylinder. Okay, I will take a cylinder. Do we need more thicker? This is good. Let's say in the cylinder, to say piston. Yes, this is the piston. Yes, and let's say here there is some little liquid. Okay, that's the little liquid here. Little liquid. So here, little liquid. here, let's say. So this is the piston. So if you need some mechanism here, this rod. Somehow this is a piston, let's say. This is a piston. And you're moving this piston. Now, you're moving this piston up. Okay? And let's say the velocity. Very high. Okay, very high velocity. Means it is quite, how to say, quite fast movement of this. Okay, quite fast movement of this. Quite fast movement of this. And how to say here. Okay. Let's say without thinking that much. Without thinking that much. Because of this movement. Okay. This immediate push. Let's say you are putting this extremely fast. Okay, extremely high. High. So this is moving up. Okay. This is moving up. What happens? Let's see. The temperature here is the same. Okay, temperature here, it's 20. Okay, temperature here, it's 20. Okay, temperature here, it's 20. And let's say what happens is there will be a moment at 20. Okay, at 20. At 20, the molecules, okay, the molecules starts something like boiling, okay, something like boiling. Something like boiling. At 20. See, like this. Okay? See, like this. Why? Because when you lift this up, there is a vacuum. There is a tendency for a vacuum creation. Vacuum means low pressure. Okay? Because vacuum may not be there just like you cannot have this way, just vacuum here and here water. No, there is no such thing. If there is a vacuum, for sure, these water molecules escapes. So starting, okay, these water molecules escapes. So that is how it's taken place. So this is all of a sudden, if this happens, what is this? This is also we call flashing. This is also we call flashing. Okay. So move down here. Extremely high velocities. At no time the piston is moving. Okay. So what happens is more gas, less liquid. Now this may be 10. Okay. Now this may be 10. Now this may be 10. Because of this flashing. Why the temperature is dropping? Why the temperature is dropping? Because gas means energized. Energized. Okay? Energized. Compared to liquid. Energized. Somehow energized. Okay? Let's say here this drops to 50. Instead of 20, I put 50. Because this energizing of the molecules formerly in the liquid phase, the energy is received from where? Energy is received from the liquid itself. So this is releasing energy. Okay, this is releasing energy. releasing energy. Okay, releasing energy. More gases. More and more releasing energy. Okay? And if this move further, okay? If this moves further, more space occupied. Of course, molecules from the liquid. Temperature further drops. 5 degrees. More energy is releasing. Okay. Energized. Okay. I think the best is to have this way. Yes, like this. Can you imagine this? Can you imagine this? So here to here, the time, if you think of time, here you have delta t. I will take the same delta t here. Almost zero at no time. Okay? Almost zero at no time. Quite interesting. Okay? Quite interesting. So, I have a little question for you and me both. Okay? True, the piston is moving. But why this water or liquid need to occupy this space? Why can't this vacuum let it be vacuum and water be there? Okay. So why it's trying to occupy that vacuum? Yeah, I don't know. That's a nature's behavior, but it's a question, of course. Yeah. Why not the vacuum be there? Hmm. with the liquid. Yes. Some cases maybe yes. If this liquid is mercury, it may be different. The heavier molecules, bondage may be more, somehow heavy, and it won't, uh, of course, evaporates. It won't evaporate. But why this evaporates? What happens to this water? Okay, that's why these liquids all have something. I can get this from here. A phenomena called boiling. But standard boiling takes time. But here now the boiling, this is the phenomena. Yeah. But here the energy received from the liquid itself for this case. Same liquid itself. So liquid temperature drops. Okay, so the liquid temperature drops. So this is, we would say, low temperature boiling. Boiling. Okay. Energy receives from the liquid itself. Here, for this case. So low temperature boiling. So I put here, instead of energy, I put here at low pressures. Okay. What low pressures? Low saturation pressures. Okay. I put saturation within bracket. Okay. Low saturation pressure. So the vapor and liquid together, that is what's the situation. So this can be saturation conditions, of course. So this is the situation. I believe you can understand this. Even I'm learning this one. Even I'm learning this. Yeah. I would say quite nice this. Okay. So this is the flashing. So this flashing effect is the basis of vapor based refrigeration. Okay, this is a basis for a refrigeration technology. This is a basis for refrigeration technology. So this is a very popular technology. Yes, a basis for a refrigeration technology. So they are using this strategy of cooling. Yeah. A strategy of cooling. Okay. Yeah. A strategy of cooling. So they are using this. Strategy of cooling. So, as you have some experience, may I ask, in the vapor compression means the standard, this air cons and the refrigerators, where this flashing is taking place? Let's say in your household refrigerator. Okay, so I'll put this question to you. Okay. In refrigerator, where is this flashing taken place? Okay, Buddha. So this is the question. Okay. In refrigerator, let me save this file. Flashing. Yes, Lamai. Can you answer this? Can you answer this? Piris Buddha, you are on top anyway. Thank you for your presence. Yeah. So, do you have any answer for this? Yes. Ruben?
Yes, sir.
Yes. You have any answer for this? Refrigerate?
Question is not clear.
Yeah.
So in expansion valves,
Yeah. Let me comment. Yeah. So we have BD, Chandana.
yes, sir.
කොහෙද මේක සිද්ධ වෙන්නේ in the refrigerator?
So expansion valve की
Yeah. So let's see. So we will look into this answer. Okay. We will look into this answer. In a different way. You may be right. Somehow you may be right. Yes, this is a familiar slide for you. The return ready. Okay. Return ready for the evaporator for loading. Of course, by right, refrigerant should be cold or the transport should be cold. Okay. So this will be taken place here at the component, okay, relevant for transport, return ready for loading. Okay. So I will put here in the text box, maybe this. Again, put this one. Yes, here, this component. So this possesses the flashing effect. Okay, this possesses the flashing effect. Flashing effect. This is for flashing effect, but any other places, if the flashing is there, that is not desirable. Okay, so let me tell you the reason. Flashing effect. If happens in a flow, okay, flashing effect if happens in a flow, let's say originally you have this flow, okay, this is your pipe, okay, okay. If flashing effect taken place, let's say not that big, but okay, like this. So what happens if this flashing effect taken place? Yes. Sorry. What happens if this flashing effect taken place? Of course, it has to follow the pipe shape. It may occupy a huge space with, okay, with high pressure, okay, with high pressure. So there is a blockage. So instead of that, what happens is because of this, if this experience a suction, I think this is not the proper place to draw everything. If this still needs to flow, okay, if this still needs to flow, okay, I will do this. This is a pipe. There's a flashing, the potential. Now all of a sudden, because of pressure drop due to some reason. So what happens is, okay, because of this pressure drop due to some reason, there will be more liquid and tiny. Okay. So this is how this should happen. You can have better imagination. So this is the potential. So this exceeds the volume. Okay, this exceeds the volume. So this has, at least since it cannot have that bubble shape because it exceeds the boundaries, so this can be something like oval shape filling this. Okay, so this is the issue. You have to be very concerned when you design expansion devices. Okay, expansion valve, this has taken place capillary throughout. Okay, it's a gradual. The flashing is gradually taken place along the length of the capillary. Okay, flashing effect. Yeah. Expansion valve, of course, it's almost a sudden because of that restrictions. Yeah, it's a tiny pinhole-like thing, and the, anyway needs to pass this refrigerant flow somehow because of this compressors, the powerfulness of suction or receiving the transport, but against there is the metering device, so there is a huge pressure drop. So the flashing is taken place, okay? So that's why if you are going to design a metering device, you have to be very knowledgeable about this flashing effect, okay? You may be using the catalogs for the expansion devices, but it's good to have this knowledge, okay? One more thing. If you evaporate the flow passage, if that is not big enough, okay, there can be flashing effects, okay, but make sure that flashing effects is for liquid. In the flow and affect the liquid. So it can be liquid vapor, but so this is can affect the liquid, not for the gas. Gas has no flashing effect. Generally for the standard cooling technologies. So whatever liquid there is a flashing effect. That's why. If excessive pressure drops are there, if the passage of the evaporator is not, the cross section is not that wide or big enough, there can be pressure drops. So the liquid, instead of evaporating by receiving heat or by loading, instead of that, yeah, of course, refrigerants in the evaporator is to receive the heat load and then to evaporate. But if there is a pressure drop, instead of receiving heat load, it naturally evaporates without receiving and finally becomes no use, that evaporated ones. That's why. So in the evaporator designs, it is very important. And also when you do the charging or when you fill the refrigerant, if it is overcharged means the pressure drops, leading for this kind of situations. So to understand everything, knowledge about this flashing effect is important. Okay. Flashing effect. I will modify this topic. So කලින්ම පොඩ්ඩක් explain කිරුවා වැඩි. Too many explanations, but later you will learn this. So this is where the desirable flashing effect is taken place at the transport return ready component. Yeah. Elsewhere happening, that is not desirable. Okay, that is not very good. Even sometimes condenser, maybe liquid lines, there can be flashing effects. We may not know. Yeah, so this is a very important piece of knowledge that especially for the B2 group can have. Okay. So let me continue this. So then I've got them. All looks very silent. Let's see now. I will try to see. Abuta? You are there, Anis? Abuta? Anything?
Sir, present, sir.
Yeah, very good. Very good. Okay. So let's say this phenomena. I take this out. I'm putting this here with a purpose. Okay, with a purpose. Okay, with a purpose. It is something like this. Imagine there is a little sizable, like a bleeding hole. Okay, not to say bleeding hole, but nice. And I will put a flap here. Oh. I will put a flap here. Yes. this one. And what I will do is, I will return this. I will reverse the motion. Okay? And let's say originally you have this here. So this will be closed. Closed. Okay? Now this is moving down. Then what happens is, okay, then what will happen is, this liquid here escapes. Let's say this opens a bit for the convenience. Not the liquid, eh? The vapor escapes. Okay, the vapor escapes. The vapor escape, and as a result, okay, as a result, this one, oh, sorry, not enough space. As a result, the piston will move here. Okay, piston will come here, and the gas all escapes. Okay, gas escapes. So you can have at high velocities. That is okay. Yeah. Yes. So take this extremely high out. Gas escapes, and this will be 15. Just as the same. Okay. This will be 15 as the same. Yeah. Then you are ready for the next movement. Okay. Then you are ready for the next movement. Then you are ready for the next movement. I have not that much of space here. So let me put it close. This is closed. and this is moving up. Okay, this is moving up, back, extremely high speeds. So no space with extremely high speed. Okay, extremely high speeds. Okay, extremely high speeds. Then what happens is yes. Then what happens is it will be something like this. Yes. Taking too long. Then it is something like this. As a result, okay, as a result, this temperature 15 may be dropping to, let's say, 5 degrees. So 15 turns to 5. Okay, let's see. So this is the cycle. T 20 degree turns to 15. You let the gas release. Okay. There should be something. This should be there. Okay, this way. So all now. All now like this. Okay, extremely high, and then this 15 turns to 5. So 15, here it is 15. Now, okay, this one, lift, vacuum, then you are just nice. Okay, just nice. Good. Escaping the liquid, fully escaped. After that, moves up, and again this way. So this cycle can be go on. Okay, then you moves this down, moves this down, and come back here. Of course, at 5 degrees C, and 5 degrees C will drop again. Okay, and this can be drops further. Let's say minus 5 degrees C, and this cycle can be go on. Okay, this cycle can be go on. So this is, I think, one of the technologies they are using in example, nitrogen liquefaction. They are using nitrogen refrigeration example. So this can be a cold head. Okay, so this can be a cold head. This one. So this can be a cold head. Okay, so there can be this evaporation, means once this is totally evaporated, this flashing is no more, but there should be some way of continuity. There should be a way of continuity. Okay, there should be. So this can be a cold head. Cold head. And this cold head can be used as a cooling source for many of the applications. So we have issues here. Escapes we need to collect all. Okay, escapes we need to collect. Escapes we need to collect all. This escape. Escape, escapes. So whatever escapes here, okay, gas formed after flashing, we have to collect all. And you are using liquid, so liquid is more cooler, so this is the cold head. So this can be 5. Then later can be minus 5. Some more afterward, this can be minus 10. Likewise, this temperature can be dropped, this cold head temperature. Okay, cold head temperature can be dropped. Even in capillaries, for the continuous cycling till stabilized, this is taken place. So this is a very good technology, really flashing. Yeah, flashing. It's a good technology. Yeah, good. The flash. Okay, so this can be continuing. Okay, this situation. So it is something like you can see evacuating this, evacuating, and more cooling. So this is some, how to say, some usages of cooling technologies, this continuous using of this effect. Yeah. So even in the linear pumps, even helium can be used as refrigerant in this kind of applications. Nitrogen, or whatever, even the high pressure refrigerants also can be used in this way. So anyway, this is flashing. Okay, anyway, this is flashing, and you know this very well. So the next is, yes, same thing. Yes, to something it's the same thing. Even your liquid, if the even your gas cylinder, household gas cylinder, if liquid coming out from the regulator, it will be very cold. Yeah. So if liquid is there, come with the, if the this cooking gas coming to the regulator and releasing is in liquid form, it will be very cold. Yeah. It's the same way, even in this fire extinguishers, whatever. When the liquid, high pressure liquid, high pressure liquid getting exposed to low pressures. Okay, high pressure liquids getting exposed to low pressures. Let's example. So one more flashing example then. New slide. So can you remember one time we used we draw some LP gas cylinder also. Let me look for fire extinguisher. Fire extinguisher. Yes.
So, excuse me, sir.
Oh, buta.
So, ඔතන වැල් එක මේ ඇරෙනවද වැකුම් එකක් තියෙද්දි ඇතුලේ උඩ පල්ලෙහා යනකොට සර්
Oh,
ඔතන දැන් අපි
වැල්
ඇතුලේ
එකක්
වැකුම් එකක් ඔව්
මේක
වැල් එකක් වගේ තියෙන සර්
නෑ
නේද
නෑ මම
වන් වේ
ඒක
වන්
නිකන් දැම්මේ පුතා.
ඕකේ
ඔව් ඒක නිකන් දැම්මේ. එහෙම මෙහි හිතලා නෙවෙයි. වැල් එකක් තියෙන්නේ එතන අර non return of the flow කියන එක. ඔව් ඒකයි. ඔව් ඒ කියන්නේ එතන මේ වැල් එකක් තියෙනවා කියලා නෙවෙයි. ඔව් මේකක් නෑ. Let's see now. I can read the label here. So let's say here for this case, what's inside. Okay. Inside here, let's say this is in liquid form. Okay. Liquid. Okay. This inside it is in liquid form. Okay. Liquid phase. Mostly. High pressure. Okay. High pressure. So this is original. Okay. Originally. So, and if you are using this fire extinguisher, okay, and if you are using this fire extinguisher, my knowledge on fire extinguishers are not very good. I've never used a fire extinguisher. This is in liquid phase. Okay, and when you are using this, at the time of using, that's why sometimes we are using the properties really, matching with the applications. At the using, okay, let's say if we think of normal boiling point, normal boiling point. Normal boiling point means, okay, normal boiling points means boiling point of any liquid at atmospheric pressure. Okay, at atmospheric pressure. Pressure. Normal boiling point. Okay, we call NBP. NBP. Example, let's say water 100 degrees Celsius. Okay, this is the water normal boiling point. Okay, water normal boiling point is 100 degrees Celsius. So if water is coming out of this, yeah, will this evaporate? No, but there can be, okay, but there can be sudden pressure drops. There can be chances of getting the, how to say, escaping liquid below atmospheric because of the nozzles and all, maybe. Anyway, let me talk this one first. Water 100 degrees Celsius. So this fire extinguishing agents inside, okay, or fire retarding, okay, actually retarding agent. Normal boiling point may be NBP, maybe less than, how to say, MBP. How to say this one? The way we see this could be less than ambient temperature, normal ambient. Let's say here at the fire maybe 90. Yeah, I don't know. That's why it depends on the designs. Could be okay. Ambient during the fire time, it's quite high. Maybe less than ambient. Okay. So then once it is releasing, what happens? Flashing taken place. Because immediately subjected to low pressure, okay, and boiling point is, okay, boiling point is below the fireplace temperature. Let's say it's very close to that. So flashing is taken place. So we can see here, surely this is coming in the vapor form. Okay, so we will could be NBP flashing point or flash point. So here we cannot say flash point, but the flashing is taken place here for sure. That's why you have to hold it very tight because of the flashing, the high velocities. So there can be something like a repulsion. So you cannot simply lightly hold this. You may have, it is heavy of course. It may be heavy, but there should be some safe handling of this. Yeah, safe handling of this. Flashing can be taken place. Okay, flashing taken place. So this may be one of the examples. And another one, let's see. Instead of this, I will put oxygen cylinder. Okay. You know that oxygen cylinder should be properly placed and secured. Because in any case, if this damage, okay, if this oxygen vent damage, okay, liquid phase high pressure. So not like this then. If the oxygen vent, V-E-N-T, oxygen vent, broken, let's say. That's why we have a regulator. What happens is uncontrolled flashing. Flashing. Okay. Causing a jet-like high velocity stream coming out. because of the flashing. Because oxygen normal boiling point is very low. Okay, boiling point at atmospheric pressure. Oxygen is very low because under ambient condition, oxygen is in gas form. Later I will tell you oxygen normal boiling point. Today we are discussing something. Let's say NBP oxygen of oxygen. I think I have to put this, the full wording. Normal boiling point of oxygen. Am I sharing the right page? I think so. Normal boiling point of oxygen. See, minus 183. Is that so? I saw one. What is the boiling point of oxygen? See, normal boiling point. It's minus 183. So we have to bring oxygen to supercooled. Okay. So oxygen boiling point. We call normal because normal means at under atmospheric conditions, standard temperature and standard pressure conditions. It's at the atmospheric. Okay. Normal boiling point. Yeah. See in the science direct this is a scientific word we are normally using normal boiling point. So it's a word we are using. So normal boiling point is minus 180. So you can imagine this liquid boiling point of minus 180 exposing to 30 or maybe 30 degrees C, let's say. So the temperature, okay, of 200 degree superheat potential is there. So this exposing would be very violent, okay. This exposing would be very violent. That's why there is a rocket effect. So that's why you have the rocket effect. So you have to be rocket effect. Rocket flying effect. So you have to secure it very well, otherwise this is disastrous. Okay. And also because of this flashing effect, so health and safety, environment safety, no issues, health and safety. There is a concern related to oxygen cylinders. Now you know really, yeah? Health and safety concerns is very serious. Mainly the safety concerns. Okay, safety, I think out health. Safety concerns. Safety is a concern. For the same way, your cooking gas, normal boiling point. If you think of cooking gas, let's see, cooking gas. Cooking gas is propane, you know. Cooking gas. LPG normal boiling point is minus 42 degrees Celsius. Okay. Yeah. Minus 42 degrees Celsius. Okay. So LPG minus 42. So these are quite interesting. So cooking gas. Let's see our for electrogas there is another name, you know. එලෙක්ට්‍රෝගෑස් වලට හාමුදුරුවෝ කෙනෙක් නමක් කියනවානේ. මට බණින් දැන් ඔය කට්ටියව මතක් කරලා. LPG minus 42. Okay. So today is a very nice lesson anyway. For refrigeration, we have to look into another case, another time to continue this. Anyway, you should watch the video, that is very important. Cooking gas also minus 42, that's why. So whenever in the industries, when you are using pressurized liquid, okay, in cylinders and containers, whatever, the safety issues you should consider. Again here, you can see the same issue. If the LPG vent broken, of course there are gas cylinder accidents really, but people, they do not that well aware the risk of this. Yeah, because once happens, gone. Okay, so that is for sure. Even high pressure steam, it's the same, because high pressure steam, it's a different story. Energized the gaseous form, that's also because once steam hit your body 80% liquid. What's the boiling point? Let's say 100. So if your steam is 200, hit your body of 100 boiling point temperature, what happens? Do you think your flesh can be found intact? No, you will be bursted. තේරෙනවද පුතා? අහනද මං කියපු එක? ස්ටීම් ටිකක් කියන හරිය ස්ටීම් ෆ්ලෝ එකක් ඇඟට ආවා කියන්නේ ඉතුරු වෙන්නේ නැහැ පුතා. ඉතුරු වෙන්නේ නැහැ කියන්නේ your body fluids all going to flashing. If it is really you are getting a full dose of steam, it is burning is not a case, but all will be exploded. Yeah, burning is not the issue. There will be nothing left for burning. If someone get a proper dose of steam, the high pressure energized steam, somehow if exposed in huge quantities, yeah, only the skeleton will be there, the flashing effects. Yeah. Okay, so today's nice lesson, somehow it's industry lesson, happened to be anyway. Yeah, no choice, the today lecture is deviated. Okay, deviated, but will be very useful for you. So don't play fool with the gases, pressurized, or even for the high pressure or the high temperature thermal sources. If you are exposed to high temperature thermal sources, your body will go into flashes. Yeah. Because 80% is water. So those are the things. So anyway, it's a very good scientific based safety lesson finally. So refrigeration, of course, we did some refrigeration until here. Okay, so we have to continue it. So nice. So we will continue, but better you go through the video I asked to go through. Okay, then your time is valued. Yeah, because whenever important things comes for discussions, because someone asked for the fire extinguishers. So we went for oxygen, LPG, and finally even for the steam accidents. High pressure steam. For that one, no slide here, but I'll add a slide here. Just noble boiling point of water in your body. Okay. 100 degrees Celsius, I would say, because 80% water. Okay. Yeah, 80% water, and then you are the high pressure steam. Because steam contains huge, highly energized. This is the word we need. Steam, highly thermally energized steam. So this will be complete then. Ruben, are you there, Buddha? I believe so. So
Yes, sir.
yeah, very good. So your biological body containing over 80% water. Okay, so water. We are claiming it as our body, but 80% water. If this steam, okay, comes, so the highly thermally energized steam, yeah, any excessive exposure, yes, would be fatal. Reason is flashing effect. No time to burn really. Okay, good. So today lesson is about flashing. So technologies finally for flashing effect. You can develop the solutions for many liquefaction of volatile gases, even nitrogen, oxygen. So you can look into the technologies, and here we will consider for refrigeration. So understand flashing effect very well. You can develop capillary solutions in as a replacement for expansion valves. One-way expansion valves are expensive. The other way, those are very sensitive. The third, you cannot touch the expansion valve for any modification or anything. You have to use as it is. But capillary, if you know flashing effect very well, instead of expansion valve, you can use capillaries. That's why all the refrigerators, no matter how high tech, so no matter how branded, all this European, even Japanese, Koreans, this LG brand, Samsung brand, whatever, all are containing capillaries there to get this flashing effect and thereby to get the transport cooled and returned ready for loading. Okay, so that's why the flashing effect is very important. If you know flashing effect very well, you can design capillaries. Even I have done some computer codings programs for capillary designs. Yeah. So that is very important. Because you should design the components. You should not buy the components from the market and fix it. That is not the way to do. You design it and use it. That's why, so for the design point of view, you have to do extensive calculations. So programming is very important. Computer programming, because there are a lot of iterative, repeating calculations. You have to convert the refrigerant property data into correlations, equations, and all. And you have to do a lot of maybe element by element analysis. So programming is essential. That's why you should learn programming not just for the sake of passing the module, but to make use of that. Even we are old people, we know how important coding and the programming, and even we do those. So the same way you should also learn programming very well. Programming is easy. It's a tool really. It's a way of doing the things easier when it comes to calculations. It is not to make your life difficult, but to make your life very easy and comfortable. Yeah. When I worked in the industry, my strength is programming one way for the thermal systems. Yeah. So later we will discuss this, Mutala. So today it's a wonderful lesson somehow about flashing. We'll continue it if possible. Look for an extra. Now I can see question. Okay, Buddha, don't worry. You send me your project. I will help you. Okay, don't worry. I can help you for the project. So when you have this phenomena as the knowledge, yeah, you can be a solution providers. Okay, so we should be very active and positive, and we should not be passive. Eh? Yeah, so you should be technologically strong. So these things will help. Hasita, I know it. Yeah, Ruben and all. Can you arrange extra class if possible this week, because we discuss only the flashing today. So since we have limited timing, if possible, if you can arrange a session today as an extra session, we can complete what we have planned today. Mechatronics group? Yeah, I can see mostly mechatronics. පිරිස් පුළුවන් පුතා චුට්ටක් කතා කරලා ලෑස්ති කරගන්න.
F ඉන්නවා සර් පියන්ද
හ්ම්
F ඉන්නවා
තුෂන්තද
සර් F අයි
පුතා මේ ප්‍රියන්තනේ ඔව්
පියන්ද
ප්‍රියන්ත පුතා මේ පුළුවන් නම් කතා කරගන්නවද මැනුෆැක්චරින් එක අපි සෙෂන් එකක් ගන්න this week 2 hours වගේ even after working at night also okay if you can
හරි සාරි
ඔව් පොඩ බලන්න ප්‍රියන්ත එහෙනම් පුතා වාගේ මට ඊමේල් ඇඩ්‍රස් එක මට ටෙක්ස්ට් කරන්නකෝ මේ ටෙක්ස්ට් කරන්න මගේ ෆෝන් එකට මගේ නම්බර එක දන්නව නේද ඔව්
කවද්ද සර් කිව්ව දවස
මේ සතියේ දවසක බලන්නකෝ after 6 වගේ නම් any day is okay any day is okay even today also after 6 I'm all right if you are okay so ඒ වගේ බලන්නකෝ ඒ කියන්නේ අපිට අද මේ කරගන්න බැරි වුණා ලෙක්චර් එක හරියට හරි නේද right so because we learned something important so we went along that direction so lesson is quite okay and you have learned something but we have to connect this to refrigeration and we have to do that refrigeration part in style so that's why I talk about flashing first so please arrange a timing maybe 2-hour session is okay and you need to join the session seriously somehow so Priyanta Puta please try to check with manufacturing as well and arrange 2 hours timing okay yeah so not at the end of the week but even if possible maybe immediately possible then it is very good so okay then hadnera putala right so let me stop the class then very good again මේවා ගැන කතා කරනකොට when we talk the technologies blend with the theories and all the ideas will come really even some students not only the B2 some B1 students are doing projects you know yeah they are sharing with me they are doing this heat pump this and that and even they are sending the photos and all they are really excited to learn in this way the practical people okay Bhutana Priyanth then please arrange a class thank you so see you soon Bhutana so let me stop the class bye then
බයි සර්
bye Bhutana
Thank you, sir. Thank you, sir.
very much bye
thank you sir
also wish you all happy new year I think this is the first time we met for this year okay thank you okay
Same to you, sir.
okay
same to you sir